All right, so we're on page 83. Have it out, have it out, have it out. Dude, what happened? He's in your seat. Get over it. Let's start class. All right, comparing distributions. Okay, so this takes place when you have two different things that you're going to do. It's something with two different bowlers. I think we're going to do an apples and oranges type of thing. So on page 83, everyone's got the book up? Nope. Book. Book. No book. 83. All right. All right, you guys figured it out. You got like 2 seconds. All right. So it says two bowlers form a team, and both of them individually have normally distributed bowling scores. They each have their own mean. They each have their own standard deviation. Okay, all good. Yeah, peace in stirrups room again. Till tomorrow. All right. So it says that bowler A has an average of 140, standard deviation 15. Bowler B has a average of 100, standard deviation 20. They form a team. Can we model this if we use both of the things? And the answer is yes. So, you have bowler A, bowler B. Bowler A has a mean of 140 and a standard deviation of 15. And bowler B has 100 and has a 20. Okay, so being that both of these scores are saying they're normally distributed, Lions no book, or is it hiding? Oh.
Sorry, I'm late.
Moving boxes. All right, so we can add the two means together, and the mean will just adjust appropriately with what you add to add. And then the standard deviation has a little extra to it where it kind of looks like the Pythagorean theorem. It's like, dude, you're pulling that out on us? Yeah, sorry. So the combo mean is just going to be 140 plus 100. And if we add things right, you get that. The combo standard deviation is going to be the square root of 15 squared plus 20 squared. And, well, hello. Sneaking by me. Okay. We're on page 83. Yes, it's all in the book. Page 83. All right, so I'm just going to jump over to Desmos real quick. So if I do 15 squared plus 20 squared. All right, so if we do 15 squared plus 20 squared, take the square root of it, we wind up getting a new standard deviation of 25. So the new standard deviation becomes that, okay? So this is something that you could sit there and start testing. This kind of could go into like a sports statistics thing. You know, if you have team A and team B, you know what the average is, standard deviation is. You know, is someone going to do better than somebody else? Okay, so does this all make sense that we've done? Pretty simple. I mean, you can find it in your book if you need it. So our goal for this week is we will finish this chapter. We will have a review on Wednesday, and then you'll have a hopefully it'll work this time, a video review on Thursday because I have a district throw up my mouth meeting. On Thursday and Friday we'll do the test on this stuff, which is good to go. All right. All right. So the next page talks about. The next page is basically talks about if both bowlers bowl 3 games. So you get the 140, 140, 140, the 100, 100, 100. That means that they're bowling 3 games. That you would expect their average to be 720. Because you just basically add those up, and then the standard deviation, look how kind of spread out that is. So the standard deviation changes to 43.3, where you'd have the square root of 15 squared plus 15 squared plus 15 squared plus 20 squared plus 20 squared plus 20 squared. So it says the team score would be 720 with standard deviation of 43.3. And then it says a note about independence. Calculations demonstrated in this assignment and technically throughout this chapter must be independent. Independent is a topic to be explored in later chapters more thoroughly, but it's noteworthy here because without independence, these calculators can't be trusted. Okay. So independence is a hidden assumption behind many probability calculations, statistical procedures. In a nutshell, independence suggests that each observation in the random selection is from a normal distribution, must have no effect on each of the resulting observations. If a high bowling score is selected, for example, it doesn't increase or decrease the chance that the next game will be a high score. This is independence is kind of a powerful thing, and once you guys get the opportunity to maybe go to a casino, a lot of times in a casino they have the idiot boards up. So if you walk by a roulette wheel, it shows you where the marble landed on the past 100 spins, because they want people to think, oh, the marble remembers where it went. Okay, they also do the same thing as far as, blackjack tables go, how many blackjacks happened. Like, again, cards don't remember, dice don't remember, marbles don't remember what they had. So independence means the probability of one thing happening, if you already knew averages from a normal distribution, if say the guy that with the 140 game had a 180 game, that doesn't mean his next game is going to be another 180 game. It's going to regress back to what the mean would have been. Okay? Yeah, technically a person could have a really good night of bowling. Okay? Maybe the chicken wings and loaded fries were perfect that day, so the bowling ball slipped off their finger just perfectly because they had greasy fingers from eating all the fried food. All right. So independence can be violated in a number of ways. In the bowling example, misreading. What if the low score is evidence that the bowler is feeling sick and will probably continue?
What's up, man?
Will probably, continue to do bad. What if the bowler using a new ball, different weight, is undetermining the normal distribution? We must be able to assume the distribution this way. So, where this kind of turns, in all kinds of things is this. The 140s is bowler A, the 100s is bowler B. So then we're going to start looking, is there a chance that bowler B could have a better game than bowler A? And the answer is yes, and that's what we're going to head into on tomorrow. Excuse me. So, as of today, all you're doing is if you combine distributions, so if you have event A and event B, and they're both normal, that means that A and B can have a new mean. They can have a combo mean. And then standard deviation of A and standard deviation of B can indeed take place. As long as we want to find the combo standard deviation, you're doing Basically, it looks like the Pythagorean theorem, but can really go on steroids. So it's pretty simple assignment on a Monday, which is great. Tomorrow kind of gets a little more meat and potatoes to it than we had. Anything more on this page? Okay. So, all right. You guys ready to do a little work?
Page 195.
All right. Let's work a couple of these while we can. Let's take a look at page. What page are you on? What page? 197. Let's do a couple of these. Make sure you feel comfortable with it, because I do want you to have a good thing. Page 197, you said? All right. 195. All right. Page 195. All right. All right. So it says the weight of apples is normally distributed with a mean of 85 grams, standard deviation of 12 grams. Provide a shaded normal distribution for each of the following. What percentage of apples have a weight greater than 100 grams? Okay, so this is where we definitely have to jump onto Desmos so we can work it. Okay, so let's get rid of this. Normal distribution. Okay, they said 85 grams, standard deviation 12. Okay, so you hit that. There's our normal distribution. What percentage of apples are greater than 100? So I'm going to go 100 to infinity. So you're talking about roughly 10.6% of the apples. If you're randomly selecting, you have about a 10.6% chance that they weigh more than 100 grams. It says you buy 2 apples, what percent of pairs of apples will weigh between 155 and 180? Okay, so on this one, we have to change our normal distribution. We go 85 times 2, because 85 plus 85. And then our standard deviation is going to be the square root of 12 squared plus 12 squared. Okay, so that basically changes our normal distribution somewhat. Okay, of course I did the math already. 85 times 2 is what? 190? 85 times 2, 190? 80 plus 80 is 160, 170. Yeah, you're right. Thank you. And then 12 squared, 144, plus 12 squared, 144. So if I wanted to figure this out, the square root, come on, of 144 plus 144, because that's 12 squared, is 16.97. $16, not 19, 16.97. So this is when I'm choosing 2 apples. So what is the chance that our apples are between 155 and 180? If I grab 2 apples, what's the chance that they happen to weigh greater than that? So I bound the region. So I have a 53.4% chance that if I were to grab 2 of these particular apples at random, that the weight of those apples will be added together will be between 155 and 180. Okay? And then number 3 says the following question pertains to bags of 6 apples. Okay, so 6 apples. So if we add 85 times 6, or 85 added to itself 6 times, so this is going to change my mean to 510. And then my standard deviation is really going to change quite a bit. So plus 144, plus 144, plus 144. 1, 2, 3, 4, 5 plus 144. So then we get to a standard deviation of 29.39. All right. So it says, what is the mean and standard deviation of 6 apples? Well, 6 apples, the mean is going to be 510, which I have up there already. And then the standard deviation is 144, 12 squared, added to itself 6 times. You take the square root of it, it's 29.39. And then it says, what if you buy a bag at the 90th percentile? How much does the bag weigh? Okay, so does that 90th percentile go down here into the limits, or do we have to change it? I do have to change it. I have to change it to, I have to go dot inverse CDF. 90th percentile is 0.90. So that means if I were to buy 6 apples, if I wanted to find out exactly the 90th percentile, what it would weigh, those 6 apples added together would come up with a value of 547.66 grams, or grams. Okay. So again, when you see percentile, you got to take a look at it. Story time, here it comes. All right, so what's the difference between the 90th percentile and then doing both of these 2 problems down below? That one I had to use inverse CDF. Do I use inverse CDF for either of these? No, these are not percentiles. So this has to go back. I have to get rid of the inverse CDF 90, and then I have to just change it. I just have to change it to go back to my limits. So the first one for C, what percentage of these apples will weigh less than 500? Okay, so I'm going to get rid of that. Goes to infinity. Max is 500. So we're talking about if I were to grab a bag of 6 apples at random, the chance that my bag of apples weighs less than 500 grams is going to be 36.7%. No kidding. Should have given her that swivel chair so you can turn around. All right, so what should I do for, it says bags are rejected if they don't weigh between 470 and 530 grams. Okay, so I'm going to change this to 470 and 530. So if they weigh a bag of apples and it doesn't come into this weight class, you're talking about 66.5% of those weigh in that range. So I'm going to go 1 minus 0.665. So it means my store is rejecting 33.5% of them. I do the complement of it. I have to subtract 100 or 1. I have to subtract 100% from the percent or 1 from the decimal. So that's basically everything that's taken place on that problem. So
wait, hold on. Why don't we use why do we have to do what you just did for the 33.5?
Oh, it says they reject that don't weigh between this. So that means here
1% will be rejected.
Yeah. So this number here is the accepted amount, but this little area here and this little area here, because the whole area is 100%, or 1 minus 66 or 0.665. Yeah, so it's 33.5. So do you think they really throw those bags of apples out, or do they just repack them? I think they're working too hard to repack them. I've been to King Soopers. It doesn't matter if they have bags full of stuff or not. People unpack their bags and fill the bags with the apples they want. So I got the same apples, the same price. All right. So do you have enough information to guide you along on the back page, or to take a quick gander at it?
Absolutely.
I think you guys can handle this back page. No problem. Get a good start on it. So you can get it done. Rather than just plagiarize stirrups answers tomorrow.